Hello everybody, this is Dr. Christopher White, and in this presentation we're going to continue looking at igneous rocks. So in this video we're going to be focusing on section 5.8 of your textbook. Now in previous videos we obviously covered topics like why are magmas generated, how do magmas move through the crust, and now we need to start thinking about why does a magma cool down and eventually solidify to give us a solid igneous rock. So the first thing we need to look at are what are the factors that control the cooling of your magma? What can a magma do to lose heat? So the first way a magma can lose heat is simply by being erupted onto the surface of the earth. And when we're talking about the surface of the earth, we mean not only the continents but also the sea floor as well. Now, when your magma gets erupted onto the surface of the earth, it's obviously going to come in contact with either the atmosphere or the oceans. In both cases, what you have is a very, very hot magma coming into contact with something that is quite cold. And so this means that your lava is going to very quickly lose heat to the atmosphere or the oceans through both conduction and radiation. And so this means your magma is going to cool down very, very fast, and it's going to solidify to give you a solid volcanic rock. Now, when your magma, or should I say lava, is also erupted onto the surface of the earth, it is also going to lose heat to the rocks which are underneath the lava flow. So as we can see in this diagram here, we can see we have a lava flow trying to push its way out of the side of this volcano here. So that means this lava flow is going to be losing heat to the rocks below it as well through the process of conduction. So by erupting your lava onto the surface of the earth, you can make it cool down very, very quickly. And this is obviously going to produce quite a fine-grained igneous rock. Now, the next method through which our magma can lose heat is conduction, and this is simply the process of your magma giving heat energy to its surroundings. And those surroundings could involve rock, it could be the atmosphere, it could be the oceans. Now, typically, the rate at which heat is lost through conduction is controlled by how big the temperature difference is between the magma and the material that the magma is heating up. So typically, the bigger the temperature difference, the faster the rate of conduction. So if you try and pass magma through a cold rock, the magma is going to lose heat to that cold rock quite quickly because there's a big temperature difference, and so your magma is going to solidify quite quickly. In contrast, if we're trying to pass our magma through a material which is quite warm, so let's say it's got a temperature similar to that of the magma, well, in that instance the magma is going to lose heat more slowly, and so it's not going to cool down anywhere near as quickly. Now, it just so happens that the vast majority of the crust is relatively warm. And so this means that as our magma is moving through the crust, it will not be losing heat through conduction very, very quickly. This allows the magma to stay liquid when it's in the subsurface, and so that helps it to rise up through the crust, because remember, the longer it stays liquid, the further it can travel through the crust. Now obviously, once our magma approaches the surface, temperatures are going to start dropping quite quickly, and so as our magma approaches the surface or gets erupted onto the surface in the form of lava, it's going to start cooling down a lot faster. And obviously we know this is going to affect the textures of our igneous rocks. We know that slow cooling deeper in the crust down here is going to produce igneous rocks that have quite big coarse crystals, the ones we refer to as plutonic igneous rocks. In contrast, the fast heat loss due to conduction when our lava is erupted onto the surface is going to produce fine crystals, so it's going to produce the volcanic igneous rocks. The next method through which our magma can lose heat is through gases. So we know that as our magma approaches the surface, the gases which are dissolved in that magma can start to come out of solution and form gas bubbles, so the gas can start to escape from our magma. Now, the gases which are released are also very, very hot. And as these gases leave the magma and they travel up and get vented onto the surface of the earth, they are taking heat with them. So the loss of a large amount of gas from our rock is going to cause our the loss of a large amount of gas from our magma is going to cause that magma to cool down very, very quickly. So typically, the more volatiles you have in your magma, the faster it will cool down. So something like a felsic magma, which is typically very, very rich in volatile phases, will cool down a lot faster when the gas starts to leave it, compared to something like a basalt, which has a lower amount of gases dissolved in it. So when gas bubbles form from a basalt, a mafic magma, they will typically be less numerous, and so heat will be lost more slowly through gas loss. The final factor which can affect the cooling down of magmas is circulating water. Now, although you don't think of it, as being a particularly wet environment, the subsurface of the Earth, so the crust, is absolutely stuffed with water, and this water is contained within pore spaces and cracks in the rock. Now, what happens is when the water which is close to the magma starts to be heated up, it obviously becomes more buoyant and it wants to rise. And so if we imagine our water being heated up here, it's going to naturally want to start going up because it's getting warmer. It's taking heat from the magma and that's warming the water up. The water starts to rise, and as it rises, it starts to come into contact with cooler rocks. The cooler rocks start to steal some of the heat from the water, so the water starts to cool down. As it cools down, it becomes denser, and then it starts to sink. And so you can see we have essentially a cycle. We have a convection cell going on. Water gets heated up, it rises, it cools down, it sinks, it comes back, gets heated up again, and so on. And so this constant circulation of water is helping to take heat away from our magma, and it's helping to transport it somewhere else where it will be lost, and then the water will return to be heated up again to take more heat away. So this means typically when your magma gets intruded into an environment where there's lots of water, it will tend to cool down faster than a magma that gets intruded into an area of rock which is relatively dry. So what are the textures that we can see as geologists when looking at igneous rocks that tell us something about how quickly or slowly our magma cooled down? Well, we're already familiar with this texture. This is, of course, a phaneritic texture. So this is a texture in which we can see the crystals easily with the naked eye. The crystals are so large we can see them without any trouble whatsoever. So this is the kind of texture we would expect to see in plutonic igneous rocks, rocks that form underground through the slow cooling of a magma, creating large crystals. And so the bigger the crystals, typically the slower the cooling of your magma. Now we can see that the crystal size in this instance has dropped down slightly. We can still see the crystals with the naked eye, so the rock is still considered phaneritic, so it's still a plutonic igneous rock, but we can see that if we wanted to see these minerals easily, we would have to get our face slightly closer to the rock. So this is telling us that this magma cooled down faster than this magma here, because remember, the faster the rate of cooling, the smaller the crystals will be. So when looking at this magma, what we can say is yes, it's phaneritic, therefore it formed underground through slow cooling, but the rate of cooling was a little bit faster when compared to this magma which produced this rock over here. Now here we have a rock which is aphanitic. So this is going to be a volcanic igneous rock. Now in this instance we can of course see that there are no visible crystals, and this is telling us the crystals are therefore very, very small. So we know the magma, or more accurately the lava, must have cooled down very, very quickly. And so we already know the environments in which this is most likely to happen is, of course, when you have a lava being erupted onto the surface of the Earth, or in the subsurface when a lava is very, very close to the surface, when it's in contact with cold rocks. And this very rapid heat loss from our magma or our lava is going to allow it to solidify very, very quickly, producing a fine-grained igneous rock. The final texture is the porphyritic texture, which we discussed earlier in, I think, the first video. So in the case of porphyritic texture, we have these larger crystals, which we call phenocrysts, and they're sitting within a matrix of smaller crystals, which we call the ground mass. And we've discussed that this porphyritic texture is the result of two-stage cooling. The bigger crystals, the phenocrysts, form underground through slow cooling. Now, as these crystals form, some of the magma in which these crystals are contained gets swept up, and it starts moving to higher levels in the crust. So as this magma which contains these crystals starts to move up through the crust, the temperature will begin to drop and the magma will begin to solidify. Now because the magma is rising, it's going to come in contact with steadily colder and colder material, so the magma is going to start losing heat faster and faster, and so this means it's going to start crystallizing out smaller and smaller crystals. And so the presence of a porphyritic texture is telling us we have two-stage cooling. The first stage happens slowly underground, giving us the large phenocrysts, whilst the finer ground mass represents the magma cooling down a lot faster, either due to it moving towards the surface or it being erupted onto the Earth's surface and losing heat very, very fast. So the process of crystallizing out minerals from a magma is defined by this diagram here. This is the Bowen's reaction series, and this is arguably one of the most important diagrams in igneous geology. So what can we see when we look at this diagram? Well, the first thing to notice is we have a temperature scale over here on the left, with high temperatures at the top and low temperatures at the bottom. So as we come down this diagram, the temperatures are getting lower. Over here on the right, you can see the diagram is split up based on the 4 different types of magma: ultramafic, mafic, intermediate, and felsic. So we know already that as we move from ultramafic to felsic, the temperature of our magma is getting lower. We also know there are changes in the composition of our magma. So as we go from ultramafic to felsic, we know that the amount of elements such as sodium and potassium are increasing. So that means a felsic magma is going to have more sodium, potassium, silicon and aluminium compared to an ultramafic magma. We know that if we were to go the opposite way, that the amount of iron, magnesium and calcium would increase. So we know that a mafic magma is going to have more iron, magnesium and calcium than a felsic magma. And of course we've already discussed how temperature and composition is going to affect the minerals that we get. So what the Bowen's reaction series does is it's a way of showing us the stages in which a igneous rock will crystallize out minerals. And so it tells us this in a couple of ways. First of all, it tells us what minerals do we expect to find if a magma of a certain composition begins to crystallize. So let's look at the ultramafic field up here. Okay, so this area here is going to be our ultramafic field. So any arrow in that field is going to represent a mineral which could occur through the crystallization of an ultramafic magma. So we can see that the crystallization of an ultramafic magma could give us olivine. It could give us pyroxene, because we can see there's a bit of the pyroxene arrow in that field. And it can also give us calcium-rich plagioclase feldspar, because we can see a bit of the plagioclase feldspar arrow is also in that field. Now, the other thing the diagram tells us is it gives us relative abundances. So the proportion of the arrow which is present in that field says how common or uncommon that particular mineral is going to be. So if we look at the olivine arrow, we can see that a very large proportion of the olivine arrow is present in the ultramafic field. This tells us that we would normally expect ultramafic rocks to contain a lot of olivine. In contrast, only a small portion of the pyroxene arrow and a small portion of the plagioclase feldspar arrow are present in the ultramafic field. So this would mean that yes, these two minerals will typically be present in ultramafic igneous rocks, but their abundance will often be lower than that of olivine. So you can see we're getting quite a lot of information out of the Bowen's reaction series. So as we move down, so as our temperature drops and our magma chemistry changes, we move from ultramafic magmas, which are very, very rich in iron and magnesium, to mafic magmas, which are rich in calcium, iron and magnesium. So temperature has changed, the composition of the magma has changed. So as we drop down into the next field, which is marked out here in this slightly lighter blue, what happens? Well, we can see that the rocks which are going to be produced in the mafic field are going to be dominated by a lot of plagioclase feldspar and a lot of pyroxene. So we can expect to see those minerals present in mafic igneous rocks in reasonably large quantities. The other thing we can see about the plagioclase feldspar arrow is that we would expect most of the plagioclase feldspar that forms to be the calcium-rich variety of plagioclase feldspar. In terms of other minerals which we might expect to find in mafic rocks, we might expect to find some olivine, because a bit of the olivine arrow is present in the field. We may also expect to find some amphibole, and we may even expect to find a very small amount of biotite, but a very, very small amount. So once again, we can begin to work out what minerals do we expect to find when a mafic igneous rock crystallize, when a mafic magma crystallizes, and what are their approximate abundances going to be? How likely are we to see them? So we know that mafic igneous rocks will typically contain lots of calcium plagioclase feldspar and lots of pyroxene, with lesser amounts of olivine, amphibole, and biotite. So as we move down to the next field, the intermediate field, once again the temperature is getting lower and we have another change in the composition of our magma. So once we're in the intermediate field, the amount of silicon, aluminum, sodium, potassium has started to increase. The amount of calcium, iron and magnesium has continued to drop. And so this is obviously going to lead to the formation of different minerals. So what can we see? Well, an intermediate igneous rock is going to contain a lot of plagioclase feldspar, but this plagioclase feldspar is going to be more sodium rich, so it's going to be towards the sodium end of the scale. And so what we can see here is that our intermediate rocks are going to have lots and lots of sodium rich plagioclase feldspar. We are also going to have quite large abundances of amphibole and biotite as well. There is also the possibility of a small amount of pyroxene, although to be honest, pyroxene is relatively rare in intermediate igneous rocks. Finally, as we move down into the felsic field, we're at the lowest temperature, and we know our magma is now very, very poor with respect to calcium, iron and magnesium, but it's now very rich with respect to silicon, aluminium, sodium and potassium. So obviously the minerals we're going to get are going to be, lots of potassium minerals and lots of minerals that require lots and lots of silicon and aluminium to make. So we start seeing the appearance of potassium feldspar, which is a potassium mineral, muscovite mica, which is also a potassium mineral, and quartz, which as we discussed earlier is due to the leftover silica once all the other minerals have formed. We will also see small amounts of amphibole in some cases, we can see small amounts of biotite, and we will also see small amounts of sodium-rich plagioclase feldspar. Now, you'll notice that this diagram has two limbs, this limb here and this limb here. So they are defined differently. This one is defined as the discontinuous series and this one is defined as the continuous series. So what's the difference? Well, this limb here is exclusively for plagioclase feldspar. Now the thing about plagioclase feldspar is that its composition is variable. At one end of the scale you have calcium plagioclase feldspar, at the other end of the scale you have sodium plagioclase feldspar, and essentially you can have a composition which ranges anywhere along this line. So right in the middle your plagioclase feldspar would be 50% calcium and 50% sodium plagioclase feldspar. So what this means is as you move through your field, so as you go from ultramafic to intermediate to felsic, the amount of calcium is decreasing in your feldspar and the amount of sodium is increasing. Now the reason it's called the continuous series is because the feldspar will typically always be present in these rocks. There will always be a small amount of calcium plagioclase feldspar in ultramafic rocks. There will always be a large amount of calcium plagioclase feldspar in mafic rocks. There will be a large amount of sodium plagioclase feldspar in intermediate rocks, and there will be a small amount of sodium plagioclase feldspar in felsic rocks. And as we're moving down these groups from ultramafic to felsic, the amount of sodium increases in the plagioclase feldspar and the amount of calcium decreases, and it's a continuous change. As you move from ultramafic to felsic, these plagioclase feldspars change their composition in a set and continuous fashion. Now over here on the other limb we have the discontinuous series, and it's called discontinuous because you don't always have to have these minerals appearing. So if we go back to our ultramafic rocks here, what can we see? Well, our ultramafic rock will typically have lots of olivine, a bit of pyroxene and a bit of calcium plagioclase feldspar. But because it's part of the discontinuous series, our rock doesn't have to have these minerals in it. It has the capacity to make them, but they don't necessarily have to crystallize out. So you can have ultramafic rocks that contain absolutely zero olivine and are made up almost exclusively of pyroxene. You can have intermediate igneous rocks where all the ferromagnesium minerals are represented by biotite and there's no amphibole. So it's simply called the discontinuous series because these minerals do not always have to occur. In the case of the plagioclase feldspar limb, that plagioclase is going to occur, it's unavoidable. In the case of these ferromagnesium minerals, olivine, pyroxene, amphibole and biotite, they can occur, but they will not necessarily occur every time. Alright, so that's the bones reaction series, and it's a very, very important diagram, so do take some time to look at it. Please also take some time to make sure you read the textbook description as well, because that's also going to help to back up what we've just discussed. Alright, thank you for watching and have a good day.